guys hear me? Yes. Great. It is so good to be here with you nerds tonight. I'm going to talk to you guys about a project during the pandemic of finding new galactic supernova remnants from the couch. As Rory said, I am Loren. I am an assistant professor of astronomy and physics at West Virginia University. And this is my first nerd night in attendance or as a speaker. So I was told that this is a general audience, so let me dumb it down a little bit for you all. This is a picture taken from the Earth. This really bright thing up here, we call this the sun. It's really, really bright, and though it's tempting to don't look at it with your eyes, it is the closest star to the Earth, and it's really nice. It provides light and heat and all good things, so thank you all to the sun. These other things we call clouds. They're up in the sky. That's a different lecture. And then the blue stuff is the sky itself, or actually it is dust that is reflecting the starlight. That is yet another lecture. So hopefully we have time for that in the future. Like all stars, unfortunately, the sun has a finite lifetime. The sun's lifetime total is about 10 billion years, and so far the sun has used up about 5 billion years. So it's kind of a middle-aged star right now. That means that the sun is about 5 billion years left. And if you have a voice message on your phone right now about extending extending your car's warranty, you have just enough time. 5 billion years will allow you to extend that warranty. I know that we're in kind of uncertain financial times. Why not just call the guy back? He was nice enough to leave you a message. When the sun eventually dies, it's going to be a very sad day on Earth because the sun will expand into the Earth's orbit as far out perhaps as Mars, and it will extend and blow up everything that we know and love on the Earth. So until that day, however, let's talk about some cool stuff out in space. So this is a view that you guys might have enjoyed on a very, very quiet, very distant location in West Virginia. We have many of these. This is a view of our galaxy. So that band of stars and dust, that's the dark stuff, that extends diagonally across the screen right now, that is the Milky Way. And the Milky Way has about 200 billion stars, of which the sun is only one, and about 200 billion planets, actually, kind of interestingly. Each one of these stars has a finite lifetime, and although the sun's lifetime is 10 billion years, stars that are more massive than the sun have even shorter lifetimes, and they will blow up even more extravagantly. We'll get to that in a second. Stars that are less massive than the sun actually have very, very long lifetimes, much longer than the age of the universe. So randomly in the Milky Way, we would expect stars to blow up, especially those really, really massive ones with short lifetimes. And these explosions, if the star is more than about 10 times the mass of the sun, are known as supernovae. You guys have all heard that term. When a supernova goes off, it emits this tremendous amount of light, and what's left behind is a black hole or sometimes a neutron star. A galaxy like the Milky Way will have on average about one supernova go off every 100 years or so. Our last one was about 1600, as we'll see in the next slide, so we are past due for a supernova event. Supernovae like this are the clearest indication of high-mass stars existing in the Milky Way Galaxy. And so by finding all of the supernovae that have gone off, we can get a really clear picture of how many really, really massive stars our galaxy is making. All right, one more bit of background. We are well behind on finding all of the supernovae in the Milky Way. So we're behind by about a factor of 2, and my job, self-appointed, is to find all of the supernovae that went off in the last about 10,000 years. So I'm going to find all of those exploded stars, and then in the software, I'm going to draw circles around them for science, because that's what science is reduced down to. All right, I like to liken this to a firework going off. When fireworks go off, you have this immediate bright flash of light at ignition, and then afterwards, you have a residual, kind of that crackling thing that you can feel. That crackling, we call a supernova remnant. At the initial flash of light, we call that the supernovae. The benefit of looking at supernova remnants is that the supernova remnants have lifetimes of about 100 or 10,000 years rather, whereas the initial flash is more like 100 years. So we can see the supernova remnants for a much longer period of time. That allows us to get a better census of their total number in the galaxy. I said before that we are overdue for a supernova in the galaxy. These are the most recent ones. These are beautiful multicolor images, primarily from X-ray data, of Tycho supernova remnant over here on the left. Kind of looks blobby, like you found it under the sea. That was found in 1572. And then Kepler supernova remnant on the right is 1604. These two supernova remnants are in the northern sky because they were found by European astronomers. And we have very, very good data on them at many different wavelengths. Unfortunately, that doesn't exist for much of the sky. We don't have X-ray data of this quality spread out over the entire sky. And to get data of similar quality, it's helpful to go into the radio regime. So let me play the next slide. This is what they look like in the radio, the same two supernova remnants. And you can see that we have the same basic structure, that we have these kind of blobby, spherical objects, regardless of whether we have beautiful X-ray images or more simple radio images of the same objects. So we can use radio data to get very, very high quality images of such supernova remnants. Okay, so keep that in mind. Another benefit of radio is that radio passes through all of the dust in the galaxy. I played that image earlier of the Milky Way, and we have that big, dark band of dust. And that's the dust that eventually makes stars. So it's integral to our understanding of the Milky Way. At the center of this image here is one of the most massive star formation regions in our whole galaxy. Unfortunately, this image was taken in the optical wavelengths, similar to what we use with our eyes. And there's so much dust in between us and the star formation region that we cannot even see it. If we go, however, to radio, it will pop right out, and it looks like this. This is known as W43, after Bart Westerhout, the Dutch astronomer that first found it. So, going to radio has an additional advantage of being able to get a census of objects spanning the whole galaxy. Isn't that cool? So, we have data for much of the galaxy, first of all, and then also those data can span the entirety of the Milky Way. One drawback, however, is that radio data can be very complicated for those same reasons, because we are able to see throughout the whole galaxy. We get all of the emission from objects along the line of sight. So on this image, which I played earlier, we have a little tiny red box. And let's zoom in to the radio view from that little tiny red box, and you'll see lots and lots of crap. Some of this crap we care about because it's supernova remnants, and some of the crap we don't care about for this talk because they are H2 regions surrounding massive stars. Massive stars during their normal lifetimes before they explode emit lots of ultraviolet photons. Those ultraviolet photons create plasma, similar to those little plasma toys where you can touch your finger to the edge of the glass. Kind of like that, but hundreds of kiloparsecs across. So we have these big H2 regions. They get in the way. Luckily, we know where they all are. In this image, here they all are. So once we remove the H2 regions, which are in white circles, keep that in mind for later, then we have a clear view of everything that is not circled. Those are candidates for supernova remnants, those exploded stars that we care so much about. All right, I have to highlight where the data came from for this project. This is the Meerkat telescope. So South Africa is entering into astronomy with this giant telescope array. So you guys have probably seen Contact, which is at the VLA. That's 27 antennas. It's a phenomenal instrument. I've used it many times. This is 64 antennas that are slightly larger than the VLA antennas. Meerkat is an amazing instrument. Don't ask me about the acronym. Astronomers love to kind of make up these crazy acronyms, but somehow they figured out how to fit Meerkat into an astronomical sense. So that's Meerkat. It's 64 dishes working together to make one image, in this case, of the galaxy. These data I've shown before, these are from Meerkat, and just to give you a sense of how powerful this instrument is, let's compare this to the VLA. I know we all know and love the VLA, but it is not quite as good anymore. So this is the VLA image. It's kind of like putting on glasses, your friend's glasses, where everything is fuzzy now. There's Meerkat. There's your friend's glasses again. So with Meerkat, we can find all of this detail, and we can find tons of new things that we couldn't identify before. So during the pandemic, I got access to these data through a little bit of politicking and started to look at them to find all of these exploded stars. So there's me on the couch with a borrowed friend's dog and a real dog that I own. We're all hard at work at our various tasks, be it ice cream eating or supernova remnant finding or just staring blankly at the wall. Whatever we like to do, we're doing it in this moment. This is capturing the best of us. Here it looks like maybe we found something, or at least one of us has changed what they're doing. The other ones seem pretty happy with the status quo. It turned out it was a relatively slow process. Lots of breaks, lots of late nights. But at the end of the day, I was able to identify almost 200 new galactic supernova remnant candidates. And I put candidates at the end there because we actually do need more data to confirm these as true supernova remnants. So on the top row here, these 6 images are 6 of the best candidates that I identified. You can see that they look like the initial objects that I showed. They're kind of blobby radio things. They're symmetric and they're relatively circular. If these are confirmed, it will approximately double the number of known supernova remnants in the survey area, which means that we will be able to close the gap between theory and observation. That's something we're always trying to do. The theory says we should have about 1,000 supernova remnants in the galaxy. We know of about 400. So adding these 200 in the survey area would close the gap for the survey area. That's a big deal. We also, of course, found a whole bunch of weird things, and these are super fun too. So down at the bottom, they might not look as weird to you as they do to me, but they don't look like supernova remnants. They don't look like galaxies. They don't look like anything we know of, and there's about 100 of those. So we'll put out a paper, publish all of these weird things. If you want to suggest a title for that paper, I'm all ears. So that's it today. Thank you all for your attention.